In this screencast, we will look at the properties of chords drawn in a circle or in two congruent circles. Our goal is to answer the question, what are two ways to determine when a chord is the diameter of a circle? The first theorem is called congruent corresponding chords theorem. In the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. What does this mean? If we look at the diagram, if these two chords are congruent, BA is congruent to CD, then their corresponding chords in the circle will also be congruent to each other. So in other words, CD is also congruent to BA. Let's take a look at an example. In the diagram, circle P is congruent to circle Q. FG is congruent to JK, and the measure of arc JK is equal to 80 degrees. Find the measure of arc FG. So, going back to the theorem, first we have to check if they are in the same circle or the two circles are congruent. It is given that the circles are congruent, and the two chords, which are the pink segments in this theorem, while in this figure they are FG and JK, the two chords are congruent to each other. Now we said earlier that the corresponding minor arcs are also congruent. So that means if arc JK in the first circle is equal to 80 degrees, minor arc GF from the other circle must also be congruent to JK. So that means our answer must be 80 degrees. The next theorem is called perpendicular chord bisector theorem. If the diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. In the figure, since the diameter EG is perpendicular to the chord FD, then the diameter bisects the chord into two congruent parts. So that means FH is congruent to GH. Now similarly, FG is also congruent to GB. Now these two theorems are converses of each other. So if you still remember, the converse of a statement or an if-then statement is true if the resulting statement when you switch the hypothesis and the conclusion is also true. So theorem 10.8, which is called the perpendicular chord bisector converse, states that if one chord of a circle is perpendicular bisector of another chord, then the first chord is the diameter. So in other words, if chord TR is perpendicular to the segment SQ such that TP and RP are congruent, and TQ and RQ are congruent to each other, then SQ is the diameter of the circle. Here is an example of the perpendicular chord bisector theorem. In this figure, we're supposed to find the length of segment HK or chord HK. According to the theorem, JL is the diameter and it bisects the chord HK. So that means if NK is 7, NH is also 7. So if we compute for the value of HK, then we would get HK is equal to twice the length of NK, and by substitution, NK is 7. So HK is equal to 14. So these two segments are congruent to each other, and you can also show some tick marks to illustrate the relationship. In the same circle, how are we going to find the measure of arc HK? Well, we know from the previous example that NK is congruent to HN, which means both of them measure 7 degrees. Because of the perpendicular chord bisector theorem, the diameter of JL also bisects the corresponding arc. So that means JH and JK are congruent to each other. So using that information, if we set these two equal to each other, we have 11x is equal to 7t plus x. By subtracting x from both sides, we get 10x is equal to 70 and x is equal to 7. So by substitution, hj is 11x. So 11 times 7 is equal to 77. On the other hand, jk is 7t plus x. So 7t plus x, which is 7, is equal to 77. But to find the measure of the entire arc hk, we have to combine the two measures together. So hk is equal to 154. The last theorem we're going to look at is called the equidistant chords theorem. In the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. What do we mean by equidistant? The distance from the center to the chord is given by the length of segment EG. So remember from the first semester, the distance between a point and a line is actually given by the perpendicular distance. Similarly, the distance from the center of the circle E to chord AB is given by the length of the perpendicular segment, which is EF. So if these two chords are congruent, then that means these two shorter segments are also equal to each other. Now, this is an if and only if statement, so that means the converse is also true. Now, let's look at an example here at the bottom. In the diagram, QR is equal to ST, and they both measure 16. Now, CU, which is the red segment, is 2x, and the blue segment CD is 5x minus 9. We're supposed to find the radius of the circle. So in other words, we want to figure out the length of this segment, which starts from the center to any point on the circle, let's say Q. So this is the radius. Let me emphasize that this red segment nor the blue segment is not the radius. A radius starts from the center to a point on the circle. So how are we going to find the yellow segment? Well, we know that since the chords are congruent to each other, QR, let me use a different color for that one. We know that QR is equal to ST. There you go. And according to the theorem, if the two chords are congruent, then that means they have the same distance from the center. So in other words, 2x, which is this red segment or pink segment here, is equal to the blue segment, which is 5x minus 9. So let's set them equal to each other. Subtracting 2x from both sides, we get 3x is equal to 9. I move the 9 over and change its sign, and then dividing both sides by 3, we get x is equal to 3. Now, if we substitute that into the equation, this 2x will become 6. So we have one side of this triangle already. Now, for this blue segment here, we know that according to the given information, QR is 16. So if we cut this into half, because we want to form a right triangle here, so if QR is 16, then half of it is 8. So using the Pythagorean theorem, this is 6 squared, this is 8 squared, it's equal to the square of the radius. In this case, QC is the radius that we're looking for. Now, you may also use another triangle here at the bottom, depending on which one you prefer. but either way you'll get the same answer because the radii is congruent from the center to any point on the circle. Going back, so this is 60 squared plus 80 squared is equal to QC squared. So 64 plus 36 is equal to the square of that. If you get a positive square root of 100, then QC is equal to 10. So that means the radius of the circle is equal to 10.